I flashed the Gradebook up on the camera, so I obviously cannot put that up on YouTube. So I wanted to stop the video and start it so I know where it is, so I can find it easily later. So I can clip it out. So what this is saying is that the top, all right, the top here keeps on going like this, right? But you're dividing it by a number that's getting bigger. This is an awesome problem because what I'm about to show you. Awesome if you like physics and things like that, engineering. Who remembers this from pre-cal? That if you're looking at the sine function in pre-cal, that this number in front was the what? Amplitude, right? And that actually told you what your bounds were, right? Like if this was a 1, then it would just be between -1 and 1. If this was a 2, it would be between -2 and 2, right? So what we're looking at right now, right, the limit I asked you to just consider was the limit as x goes to infinity of sine of x over x, right? That's what I asked you to do. And I just tried to convince you that the answer was 0, right? But I want you to look at this a different way. I want you to look at that and look at it like a function, like this, in pre-cal. But you see that x on the bottom? I'm going to slide it out in front like that. Do you all see that that's the same as this? I just pulled the x out in front as a 1 over x. Yeah? And now look at this compared to this. In pre-cal, here's our sine function. Here's our amplitude, right? Here's what is happening to that amplitude. As x gets bigger, what happens to the amplitude? What happens to this as x gets bigger? It gets what? Well, the bottom gets bigger. Fixed over. It go well. This bounds by 1, but the bottom is getting bigger, right? I'm saying is if I try and graph this, if I ask you to graph this function, it's like a sine function, right? But there's one little catch. As I go to the right, the amplitude keeps getting smaller. So it should actually be sine, but every time I move to the right, it gets less tall, right? And the amplitude keeps shrinking, doesn't it? Let me graph it. I'm going to use Desmos to graph it. Y equals sine x over x. No, not s, x. There we go. Here's the graph. Oh, you know what I should do? I should put the sine function up there as well. So the blue is your normal sine function, all right? And then the red one is the sine x over x. Do you see that it's trying to be a sine function, but it keeps getting its amplitude squished down as we go to the right? Yeah? Let me change the axis here so you can see that. Let me. What the hell? There we go. So the blue is the normal sine function. I've zoomed it in a way that you can really see this sine function, the sine x over x, that it's trying to be sine, but it keeps on getting squished down. I'm going to show you another thing that I think is cool. We're almost out of time. Take that same thing. I'm going to graph just the 1 over x, not the sine x, just the 1 over x. And I'm going to graph -1 over x. And do you see that this 1 over x sine x actually lives between those two curves? And it's like a funnel. And it's forcing my function in between those two as I go down. So it's like I'm trying to draw the sine, but the ceiling and the floor keep changing for me. And I keep on going down like this. Yes? Oh yeah, it gets, well, how do we know it's going, wasn't that our answer? When we did that limit, wasn't the answer 0? Do you see that the further out I go, I get closer to 0? Now it's a little weird because I go up and down. I go above and below 0, right? I keep going above and below it. But the further I go, right? The further I go, you can say that it's approaching 0 because as you zoom in, there's still going to be oscillations in here, but these oscillations just keep getting smaller and smaller and smaller, so it is approaching 0. Weird function, right? Now, the reason we like that, this in engineering and physics, this is called a damped oscillator. And so think about if I take a ball and I drop a ball, what's it going to do? Bounce, come back up, bounce, come back up, right? Bounce, come back up. Well, we could try and model that with a sine function, right? Like, or something like a cosine or sine, like that. This is time on this axis, right? Time, I start with the ball here, start the clock, the ball drops, comes back up, drops, comes back up. This is not what happens in the real world though, right? Because when you drop a ball, does it ever reach the height that you dropped it from? It never can. It has to somehow, it can never come back up to the same point. It's always going to be a little bit below. You lose something, okay? So in the real world, we want something that behaves like that, doesn't come up as high, next bounce not as high, next bounce not as high, and eventually down to nothing, right? And this graph that I showed you here, the damped oscillator, is a much better representation of what's happening than just a sine or cosine curve, because it fades out, fades away. Understand? So that's a very useful function in the real world. Or not this one in particular, things that are like this. There's a lot, I can put x squared down here, I can put e to the x down here. There's a lot of things I can do to make it like vanish away faster. All right, I'd like for you to try to do all of your homework for 1.6. Well, last time I had you what, do 13 through 15, or that was it, right? Go ahead and ignore what's on our homework schedule. Focus your attention on 13 through 33. You're going to have some issues, all right? Because, you know, I always leave things in the homework for you to kind of investigate and discover on your own. But I would start with all the odds, and then when you do the odds, go after the evens. All right? All right, everyone. Have a great weekend. That class seemed long, though? That class seemed long to me. Okay. Y'all have a good one. Mind if I squeeze by? I'm just going to turn my camera off real quick.